In this video, I'm just going to go through a few examples where we calculate derivatives involving the natural logarithm. So here's the first example: y equals x squared times the natural logarithm of x, or x squared equals, or x squared times ln x. So in this one, we're going to have to use a product rule. That came out so weird. So dy by dx, it's the product of two things. It's the product of x squared and the natural logarithm of x. So we take the derivative of the first term, which would be 2x, times the second term, the second function, plus, leave the first function, times the derivative of the second, which is 1 over x. That was the rule for the derivative of the natural logarithm. And then you can just simplify this term right here a little bit. So it'll be 2x natural logarithm of x plus, this would end up being just x. So that's the derivative. If you want, you can factor it, do a common factor of x. Not really necessary, but you can. Second function, y equals, I'll go natural logarithm of, say, 3x. So here, we have to use a chain rule because we have a function 3x inside another function, which is the natural logarithm function. So the rule for the chain rule is you take the derivative of the outside function, which is ln x, or the natural logarithm of this. So instead of being 1 over x, it's going to be 1 over 3x. It's 1 over whatever is inside the logarithm part. And then you have to take the derivative of the inside, so times the derivative of the inside function, which is 3x, so it'll be times 3. And then in this case, the 3's would divide out, and you will get 1 over x. Always going to state that x must be a positive number, because that's the domain of your original function. Notice in this one I didn't state it. I didn't say x must be greater than 0. You can if you want, but because there's a logarithmic term in here, ln x, it's sort of implicit in this derivative. So the domain of the derivative is kind of obvious there, but here it's not as obvious because I don't have a logarithmic term here. Third example, this one will be a little more involved. Determine the point, let's just say determine the x value where y equals the natural logarithm of x squared minus x has a horizontal tangent. So in order to do this, we have to take the derivative of this function. It's, again, just like the last rule, a chain rule question. So the derivative of the natural logarithm, so the outside function, will be 1 over whatever's inside the logarithm. So it'd be x squared minus x times the derivative of the inside function, which is x squared minus x. So the derivative of x squared minus x is 2x minus 1. So this would be equal to 2x minus 1 over x squared minus x. And now what are you going to do with this? So we want to figure out where the tangent is horizontal, which of course means you set the derivative equal to 0. And we now have a rational equation. In order to solve a rational equation, multiply both sides by the denominator, or just look at the numerator and set that equal to 0. So 0 equals 2x minus 1, which means 2x equals 1, or x equals a half. So we get an x value of 1/2. But remember, we need to take into account the domain. And the domain is that whatever is inside the logarithm must be a positive number. Now sometimes people look at this and say, well, x equals a half, that's a positive number. But it's not necessarily that x must be positive. It's whatever's inside the logarithmic function that must be positive. So in this case, x squared minus x must be positive. So when does that happen? Well, that's a linear inequality, or sorry, a quadratic inequality. So if you remember from advanced functions how to do that, there's a few different ways to do it, but one way is to just graph the corresponding function y equals x squared minus x, which would factor as x times x minus 1, which has zeros at 0 and 1. So a quick sketch of that, I mean a very quick sketch of that. There's a 0 at 0, there's a 0 at 1. This is a quadratic facing up, so it looks like this. So the question was, when is this positive? Right? When is it greater than 0? So that would be over here and over here, which means x must be an element of, say, minus infinity to 0, or 1 to infinity, which will end up being the domain of this function. So that's the domain of this function here, which means it's also the domain of this derivative function here. That's the restriction, that x must be in this interval, which this point is not. So not in the domain. What does that mean for our answer? It means this point doesn't work. This is not actually a critical number. So because it's not in the domain. So therefore there are no points where the tangent is horizontal. Okay, so that's something you need to be a little bit careful about with logarithmic derivatives, because it's the one derivative where if you just look at the derivative function, the domain of the derivative won't necessarily match the domain of the original function. So you always have to go back and consider the domain of the original function, which becomes the domain of the derivative.